Okay, so Bill couldn't be here this morning, so I offered to step in and give his talk in his place. So basically what I'll present is a model of how water might migrate from the poles to the mid-latitudes. This is a polar fountain model to try to explain the OH veneer that has recently been observed. Okay, so 2009 was a big year for lunar science. We not only had L-cross, but also this water veneer was discovered. And basically it's a 3-micron feature seen in the infrared, checkmark-like feature in panel C there. And basically it's seen along the terminator and in very cold polar regions. And this was quite provocative. And there's even been a possible diurnal effect that has been reported by Sunshine and colleagues in 2009. And there have been several sources that have been suggested for this nonpolar water. One is hydroxyl bound to the mineralogy, and this is an evolving view because the Apollo era samples were quite dry. However, it's been suggested that insoluble water is suspended within some grains, and however, this is expected to be only a small fraction of the only cover a small fraction of the entire surface. So it can't explain the water veneer. There's also cometary and meteoritic infall, which delivers water to the surface or can dig up water. Meteorites can dig up water, turn the surface, and bring water, let water escape. And then also there's solar wind conversion, where energetic protons, about a kilo electron volt, can implant into an oxygen-rich regolith. And this could lead, like I said, to implantation. Also, at some energies, at higher energies, you have sputtering. So solar wind could be a sputtering loss if you're you have a very saturated and icy surface. So there could be a balance somewhere in between. In this talk, we suggest a fourth source for the OH veneer, and this is a polar, essentially a polar water fountain, where it's basically redistribution of water from the polar cold traps to mid-latitudes, and basically space weathering processes are they're energizing the surface at the poles to release water. It escapes, goes to mid-latitudes, hops around, and then can stick as OH. And so let's take a look at the water source in the lunar polar cold traps. Basically, we know that water exists at the poles. Instruments on LRO and Lunar Prospector really define these regions as quite wet. And this includes statistically significant neutron-suppressed regions, including Cabeus and Shoemaker. And of course, the presence of water was validated and then some by L-cross. Again, 2009 was a terrific year with this low-cost L-cross and Centaur impact, and it found 5% water weight in the plume in the form of gas and ice, as well as many other species. However, this high concentration of water is hard to reconcile with the neutron spectrometer results, and there has been the suggestion that L-cross simply got lucky and hit a pretty wet spot on the moon. So, right. So to model, to kind of take these two things into account, the fact that we have these neutron spectrometer measurements with a somewhat low concentration, the L-cross measurements with a higher concentration, we start out in this polar water fountain model with two different types of models for the source. Basically, we have this model number one. It's a surficial and subsurface ice regolith mix at a somewhat low concentration. And then we would also try a second model with where the ice is buried at a higher concentration. And we'll look at the various space weathering processes to see, try to estimate yields of water coming from the poles as a source for the OH veneer. And so we're only considering water within the polar craters. This gives us an area of about 100 kilometers squared. And the transport process is as follows. Water is essentially liberated from the poles via space weathering, and it's ejected to mid to lower latitudes. And then it migrates around via ballistic hops around the surface, like in Kreider and Bondrock and Butler. And it will eventually photodissociate into OH at which time it sticks. And it's been suggested even at greater than 400 kelvins, the OH will actually stay where it's at until being photodissociated or sputtered. So we would have both a water layer due to these particles that are moving around, and also an OH veneer through this process. So as for the liberation mechanism at the polar source, there are 4 different liberation mechanisms that we're considering. The first is sputtering, where 1 keV protons from the solar wind are diverted into polar craters via wake formation, and we can calculate the yield for this process. We also have electron-stimulated desorption. We're using the cross-section of Thrower et al. 2010. And the electron flux, again, is defined by our polar crater solar wind inflow model that we've developed at Goddard. There's also photon-stimulated desorption, where we get cross-sections, from Thrower et al. 2010, and then we apply the flux from the background Lyman alpha. And we also consider impact vaporization as a possible liberation mechanism for water coming out of the poles, and we get our micrometeoroid yield from Centella in 1992. Okay, so I have one example here of one of the processes that we are modeling, that we're considering as a source for the polar water fountain. And I showed this movie yesterday. This is basically where the horizontally flowing solar wind is deflected into polar craters via plasma physics processes. And of course, you'll see in this quick video, you'll see the solar wind flowing by horizontally. The electrons will rush into the crater in the top panel, creating an ambipolar electric field that you'll see in the bottom panel, and the ions will follow behind. And there the ions are blue, and they're following in behind. And then now we've included sputtering in this particle and cell model, computer model, and when the ions strike the surface, they can emit water molecules, which come up in the form of collisionless cloud that's ballistic. And you can see the emission. Many of the water particles are leaving the crater, and this would be one source of the polar water fountain. Okay, so skip that slide. So taking a look at the 2 different surface models that we proposed, basically this is the first model where we just have water that's on the surface or just below the surface, and it's all of these processes can get at this water. Basically knowing the yield for each process, sputtering, electron-stimulated desorption, and others, we also know the frequency of these events, so we can multiply these and get and integrate over the entire area of the water that's distributed at the poles to get a number of water molecules coming out of the poles per second. And you can see all of these processes compare within about a factor of 10 to the 17th, 10 to the 18th water molecules per second. And then we have the other surface model where we have the buried layer of water. Only impacts can access this water, and we assume this higher concentration of water at some depth D. We require the impact to penetrate farther than that depth to get well into the icy layer. And assuming a nominal impactor speed and an impactor mass, we can estimate the amount of water vapor that's created, as well as the area from which it's emitted. And so if we look at different layer depths for the ice, and also look at different masses of impactors and penetration depth, we can calculate a general yield of water that basically depends on the, it goes as the mass of the impactor over the mass of the mass of water. So using this model, we get much lower. We had like 10 to the 17th to 10 to the 18th water molecules per second coming off for the superficial water model. But now if we have the water buried and we have impacts coming in and churning up the surface and releasing the water, we get much lower much lower number of water molecules per second coming out of the poles. So there it is. Okay. So Dana Hurley has been able to model this using a Monte Carlo model. And assuming if we assume quite a liberal water flux compared to what we've calculated, this is 10 to the 19th compared to about 10 to the 18th, 10 to the 16th from these two surface models we tried. We get a somewhat correct-looking, it's a correct-looking spatial distribution of water, but the concentration levels are much too low by a factor of over 10 to the third. So conclusions are that basically we think the environment does extract volatiles from the polar crater surfaces, but not by thermal processes like sublimation. We're actually looking at sputtering, impact vaporization, and other things, which we rely on for this polar fountain model. But the water fountain cannot account for the higher concentration seen in the M-cube data. But we think that redistribution may provide some contribution at a smaller level. And we think LADI could look for the UV signature of this polar water flow. And actually, that's the end. So thank you.
Do we have any questions? I have one actually. It might be for Dana. On the modeling, what sort of energy do you use for the sticking out in the non-shadowed craters?